So let's go. All right. Please let me know if there's any problem with sound. Today's topic is still on fusion welding, but we're expanding outside arc welding. Now we're going to be talking about melting the base metal, but with a source of energy other than lasers, other than arc. In this case, I want to start with lasers. And in this case, we have this substrate, just as we had with arc welding, and we have the molten metal. That's the weld pool, just like we did have in arc welding. Here is the solidified metal as which the beam is traveling from right to left. And then we have the beam coming in, and this is what is causing melting. In this case, in which the beam is melting locally, actually, there is very little difference with TIG at relatively low currents. If TIG was running at higher currents, then the plasma jet can cause a deformation in the weld pool and can have the consequences of humping and other defects. Now, the interesting thing with lasers, and it's also true of the case of electron beams, is that if we have too high power, we don't have a plasma jet, because in this case, there is no plasma and there is no electrical current circulating in a fluid. But what happens is we have local evaporation, and this evaporation essentially drills down into the base metal. And as it drills down into the base metal and the metal evaporates, it causes a hole. That's what we call a keyhole. In some aspects, has some similarity with welding with 6010, but the physical mechanism is completely different. In 6010 is the force of the arc, what is drilling a hole. 6010 is stick welding. And in this case, what is drilling the hole is like the evaporation of the metal, and we're essentially vaporizing the metal and causing a hole. And of course, the heat also creates a melt and in the weld pool behind. So in the case of beams, we have two very distinct types of heat transfer. One is what they call conduction mode, which is a very bad name because in reality is convection, what is transferring the heat here. But whatever, if they call it conduction, we'll go with it. And the other is keyhole mode. As you can imagine, keyhole is going to be a lot deeper, and it's going to be like a deep cut into the metal. And hopefully it's not a cut, right? Hopefully that's a weld. And we'll be discussing weld penetration much more later on. But this is a schematic that relates to lasers, beams, and we'll see electron beams are very similar. How do we protect the molten metal in lasers? We typically protect it with a shielding gas that is argon. In that aspect, it's not so different than MIG or TIG, right? We are having a shielding gas. Than TIG, because this gas is seldom an active gas. This tends to be typically argon, sometimes argon with and some mixtures with helium. But all you want is to prevent the reaction of the molten metal with the oxygen and nitrogen in the atmosphere. Welding, laser welding is similar to TIG in many aspects. Of course, we don't have an arc, but this can be autogenous if we put no filler wire, and works very well. If we want to put wire, would be much the same as it is in TIG. In this case, we can have a cold wire or a hot wire. And something that actually also is occasionally done with TIG too, is to run it as a hybrid system. So for example, in the automotive industry, it's common to have a tandem of laser and gas metal arc welding, right? If the gas metal arc welding goes in the front, it melts the metal, so we would not have a gap, and the laser comes back behind and makes it deeper. lasers can also be used for cladding. In that case, the filler wire is powders, and although on occasion it can be also hot or cold wire. In our lab, we have a laser, a very powerful laser that uses powders as filler metal. And in the case of additive manufacturing, which is when you do additive manufacturing metals, it's a family of processes called directed energy deposition. You can often blow powders either from a nozzle, or you have powders in a powder bed, what is called selective laser melting. And you can also add hot or cold wire. And that way, layer after layer, you create a component. In the case of lasers, of course, polarity doesn't matter, because we're not talking about a flow of current at the point of energy transfer in the welding process. What characterizes laser beam welding? Well, number one, very expensive. If you think you can do oxyacetylene for buying, I don't know, less than $1,000 in equipment. You can do MIG also on the, or stick on the cheap. When you go to laser beam welding, right today, you have to think something about $50,000 per kilowatt if you want to buy a laser. Right? A few years ago, it used to be $100,000 a kilowatt. In our lab, we have a 9 kilowatt laser. So you can go on and do your numbers. It's not a cheap process. Another thing, laser must be automated. There are two reasons for this. The first reason is a reason we have already discussed, in which it's such a concentrated energy source that the residence time is very short, right? The amount of time the beam is over any particular point in the weld is very short, and is shorter than the reaction time of a human being. So if you try to weld by hand, you end up making a big mess. So laser welding is always automated. There's another reason why it should be automated, and it's because if the light of the beam can melt metal, for example, can melt steel, and the molten steel becomes a specular reflect, becomes the best mirror you could possibly have because it's shiny molten metal. That light of the laser that bounces off the weld pool and is so perfect, just as it could have cut melted steel. If it hits the welder, it gets into a bad problem. To give you an idea, in our lab, it took us about a year to finally get a permission and meet all the safety standards for operation in the university. And you know how it works? The laser is in a room and all the operation is outside. So for sure, you don't want to be holding a laser with your hands. Even in automated cases, the reflection of the beam can come back, and a funny thing, if the beam is aiming against a flat surface, the reflection can come back in, and the laser would be committing suicide, would be killing itself with its own power. That's the reason why in many laser operations, when you weld on a pipe, the laser is a little bit off center. So if there is a reflection, it doesn't come back directly into the laser. Something interesting about lasers is, although we say it's a high energy density process, and it can even be a high power process. 9 kilowatts is high power. High is like welding, an arc at 9 kilowatts is a very big arc. However, because it moves so fast, the amount of heat per unit length, right, the heat input, which we discussed in terminology, tends to be low. What a paradox. You have a powerful process, but that gives you low heat input. And low heat input means low distortions. Also means very fast cooling, which can be a problem in some cases. Laser can make very small details. So for example, when you're doing laser cladding of components with complex geometries, the lasers are ideal to go around and make the fine details in a way that PTA sometimes can, but if the details are too fine, it cannot. The energy transfer in lasers is very low. First of all, depending on the type of lasers, I'll discuss in the next slide, but to get 1 kilowatt of laser energy, sometimes we need 5, 10, or more kilowatts of electrical energy. So we dissipate about 80%, sometimes 90, sometimes even more. We waste all that energy, electrical energy. So lasers are very inefficient in the generation of energy. But in addition, if you think, isn't it crazy that we're trying to put energy into a weld, and the weld is a mirror, and what we're using is a light, right? We're trying to put all this energy in the form of light, and it's onto something that is the best possible reflector, right? So lots of the energy bounces out of the laser, right? It's the energy that, when it bounces back, can fry your laser up or can cause you bad injuries. I have a question if the low heat input per unit length is due to the narrow arc. The low heat input per unit length is mostly due to the high velocity, the high travel velocity. And this, there is no arc in laser welding, but it's true that the penetration of the weld can be deep and narrow, but that is more of a consequence of the low heat input than a cause. Essentially, what I put here, let's use the pointer. Here. Okay.
In laser.
Sorry, I was forgetting about my laser pointer here. Talking about lasers, and I was forgetting about my laser pointer. So high melting efficiency means that the energy that comes into the plate is mostly used to melt the metal, and it's not dissipated into the component, your base metal, causing distortions. Applications of laser welding. Okay, first of all is only shop welding. Although there are current conversations about doing portable welders, but I can tell you something, the technology, not trivial, but I definitely feel we can get a hold of it. Safety issues, it took us a year to commission a laser inside the room. Can you imagine the nightmare that it will be to try to commission a laser that can be taken elsewhere? I'm sure it's possible, and by the way, it will be done. And by the way, it's something that the type of thing we should want to do in our province, because we have so much need. Even if oil and gas go away, we still have an enormous infrastructure that requires maintenance. And very often the maintenance would be best done with an internal cladding of a, for example, of a vessel. If we could automate it and use laser welding, that would be fast and ideal and cheap. It would be a good way also of exporting our technology and expertise and make up with our knowledge what we're losing in natural resources right now. Applications, very high value-added components. If you remember when we discussed in class number 1, that what enabled the Airbus, the big Airbus, the A380, to be so big was the use of welding instead of riveting. And the welding they used is laser welding, right? And it took a lot of effort to get to that point, and it takes a lot of effort to make it work. But it's worth it because an airplane is so expensive. The other type of application in which lasers shine is when you have large manufacturing volumes, for example, in automotive. So lasers are quite a bit used in the automotive industry. And it's not that cars are so expensive, but lasers enable to do a very, very fast weld, faster than we could do with an arc.
In laser beam welding, the heat for coalescence is generated by a focused beam from a gas or solid-state laser. The most commonly used gas laser is the carbon dioxide or CO2 laser, which is actually a mixture of carbon dioxide, nitrogen, and helium gases. The most commonly used solid-state laser is the neodymium-doped yttrium aluminum garnet, or YAG laser. CO2 lasers can generate greater continuous beam power and are suitable for welding thin or thick workpieces. YAG lasers generate less continuous beam power and are generally used to weld thin workpieces. Most laser welds require no filler metal, although filler metals can be used if desired. Inert shielding gases are normally employed, usually argon, helium, or a mixture of the two. Welding speeds are usually much higher than other welding processes, thus limiting heat-affected zone size and workpiece distortion. In addition, because of the intense, precisely focused heat, welds can be quite deep. Also, welds can be made in confined regions and between dissimilar metals. Laser beam welding systems are used in many industries and are typically fully automated and computer controlled. Typical equipment includes the laser and its power supply, a beam delivery system with mirrors and focusing optics, a workstation, and a motion control system to move either the laser beam or the workpiece. Many ferrous and non-ferrous metals can be joined using laser beam welding, including carbon, alloy and stainless steels, aluminum alloys, copper alloys, magnesium alloys, nickel alloys, titanium alloys, and refractory metals.
All right, very interesting. So this video that I wanted to share with you is quite old. So let me tell you two things. It focuses mostly on CO2 welders and the YAG lasers. Both of those are pretty much obsolete for welding purposes. Isn't that crazy, right? But most of the other things it said were true. So the lasers that are currently of relevance are these two types of lasers that are close cousins. This is the fiber lasers and the diode lasers, which the video I showed you said nothing about. So, but let's start with the CO2 lasers that they do mention. The CO2 lasers and are particular in that they have a very lasers for welding and for cladding work in the infrared spectrum, so we don't see it. So when in the video they were showing a little dotted line, that's the aim point in which they have a secondary laser just to know where the aim goes. But that's not the laser. The laser we never saw because it's infrared. In infrared, we don't see it. The visible range reaches to about 800 nanometers, right? 0.8 microns, 0.8 microns. Now, a CO2 laser is 10 times longer wavelength. It's 9 to 12 microns wavelength. Let's call it more or less 10. And we're gonna see this number that kind of makes sense. So it's a very, very, very long wavelength. And that has a couple of challenges. One is that metals are very reflective at that wavelength. So it has a very low efficiency. And it's so low that, for example, copper is particularly reflective at those wavelengths. And welding copper is considered extremely difficult to do laser welding of copper with CO2 lasers. There's another thing. At that long wavelength, this metal vapor that is generated, for example, in the keyhole, this metal vapor is somewhat opaque to the laser beam. So the laser starts to heat up the vapors. And when it heats up the very vapors, very much the vapors, guess what happens? We have a plasma. Not because in this case, not because we have an electric current, but we have a plasma. And this plasma acts as a shield to the light. So the plasma starts to absorb the light, but the metal doesn't absorb the light. So the efficiency of CO2 lasers is very low. It's an old technology. Some companies start just to take their CO2 lasers out. They don't care, out, and get some of the modern lasers. Just in electricity, they recoup the money. So they have an advantage though, and is that they can have a very narrow focus. So when you want to weld with lasers, you want to have a relatively narrow focus. You don't want to have a very big area of light because it all gets reflected. But if you have a narrow focus, you can create this keyhole, and this keyhole has relatively high efficiency because as the light bounces in this molten part, it's hitting the walls and acts as a cavity that is like a black body cavity. It's not a black body, but it's a lot darker than shiny metal. Another drawback of CO2 lasers, well, two more drawbacks. One is they have a large footprint. They're huge, huge. So you have a huge laser that is like a whole piece of equipment, and then you need to move the beam, right? Because you cannot have the laser too close to the component. You need to somehow carry the light. And the other thing that is not written here in the notes, but I'm making a note for adding it for future years. At 10 nanometers, there is no transparent medium that can carry that very long wavelength practically. So CO2 lasers work with mirrors. They cannot use fiber optics. So if you want that, you have your huge laser on one side of your shop and you're welding on another part of the shop, you have a system of mirrors that has to start bouncing the light until it comes down on your component. You can imagine the complexity. Also, you can imagine how any little movements can misalign the lasers. And they are a nightmare. Let me give you an example. Here in Edmonton, a company had CO2 lasers. And because they needed to go through all this set of mirrors, alignment was very difficult. And between summer and winter, when we have a little bit of frost heave and motion in the ground, you see that in the doors of your own house, the lasers would go out of alignment. That's a nightmare, right? It's an unnecessary nightmare. Now, fiber lasers and diode lasers are, from the practical, from the engineering point of view, very similar. In this case, they have a wavelength of 1 micron, a little bit more, right? But like 1 micron. So CO2 lasers, more or less 10 microns. Fiber lasers and diode lasers, like these are modern solid state lasers, are 1 micron, right? Visible range, 0.8 microns. So these are very near the visible. We still don't see it, but they're not too far away from where we could see. Now what happens? At this wavelength, the laser doesn't couple with the vapors anymore, which is rather convenient. We don't have a plasma anymore, unless we make a big mistake. But now the issue of plasma shielding our laser, not so much of a big deal. The wall plug efficiency, because this is a solid state laser, is essentially a big diode, now is much higher. We went from 10%. For getting 1 kilowatt, we needed 9 kilowatts with CO2 lasers. And now with fiber lasers, it's 30%. It's 3 times better, much better. In this case now, because at 1 micron wavelength, we can use fiber optics, life is so much better. The laser is so much smaller, so much smaller. And you bring, in addition, the light of the laser with a fiber optic in our lab is kind of crazy. You don't realize we're carrying 9 kilowatts through a little tube that has an optic fiber. You don't even realize that. With CO2s, you get to see this incredible contraption of mirrors being shielded and protected, and even a mechanical structure holding them. So this is so much more convenient, because mounting a head with an optic fiber, a laser head with an optic fiber, is so much more practical and mechanically convenient, while mounting a head based on mirrors is very difficult. The maintenance of fiber lasers and diode lasers too is very, very low. So these lasers save electricity, save maintenance cost. They use less power to weld more. So no big surprise. These things that are based on semiconductors are becoming dominant. The difference between fiber lasers and diode lasers, I'll tell you what I know, but I'm not an expert on this, although we're going to be becoming experts in the lab as we learn. To generate laser light, you need a resonant cavity for the light. In CO2 is something involving a gas where this resonance happens, but in the diode laser, the resonance happens in the diode, and if in a fiber laser, the resonance happens in the fiber, right? And that's the main difference between fibers and diode lasers. In the case of a diode laser, the wavelength is very similar. The power supply efficiency is higher. It went from 30% efficiency for fiber lasers to 50%. The beam in diode lasers is not as tight as in fiber lasers. And for that reason, when you want to have keyhole welding, or when you want to have laser cutting, you need a razor sharp beam. You tend to use fiber lasers. When you want to do cladding or additive manufacturing, you do not need fiber lasers. You can use them if you want, but you defocus the beam, right? You don't need a scalpel for those things. And diode lasers shine. Diode lasers are also quite a bit cheaper than fiber lasers. In our lab, we have something that is called a fiber coupled diode, which we are very happy and we love it. It's kind of a poor man's diode laser, a poor man's fiber laser. It's in many aspects almost everything a fiber laser is, except the beam is not as tight as a fiber laser. But we don't care because we do cladding. And on the other hand, because it's cheaper, we could have something that is much more powerful. I believe into the future, the line between fiber lasers and diode lasers is going to start erasing. Diode lasers have a very small footprint. If you come to our lab, you would see that our 9 kilowatt laser is of the size of a fridge. If you see a CO2 laser, the CO2 laser is the size of a room and needs a whole system of mirrors to go to where the welding head is. Lots of reasons to have fiber and diode lasers. And Nd:YAG lasers have a similar wavelength as fiber and diode lasers, but they are also becoming obsolete. They have an extremely low wall plug efficiency, 3%. For every 3 watts I'm getting, I'm burning 100. Not very good, right? And also they require very high maintenance, and they have a large footprint too. So what you saw in the previous video, CO2 lasers and Nd:YAG lasers, there are still niche applications for them, but what you're gonna see for laser and cladding and additive manufacturing is either fiber or diode lasers. Let me show you a video. Here we have laser welding. You see no arc, isn't that crazy? And this video has no sound, so it's okay. You get to see clearly the weld pool, right? And look at the one at the bottom. Both these welds are done in what is called the conduction mode. There's no keyhole in here. For those of you who have experienced welding, you realize how fast these beams are moving. That's why they like them in the automotive industry. This is fast and very efficient. And very clean too. Is all the cleanliness of TIG welding? Well, this is one notch up. These welds you see here too, they are bead on plate, they're autogenous welds. All right, let me show you about cladding. And this is a video we took in our lab. And if you remember when we talked about PTA, this has some similarity. Here we have the weld pool, and here we have the powders coming in. We are having 4,000 frames per second. So this is about 130 times slower than reality. The reality is 130 times faster. What you get to see here are the clad beads. Here is the base metal. Here is the weld pool, and the progression is moving from top right to bottom left. What this cladding is nickel tungsten carbide. So the powders you see coming are a mixture of nickel powders and tungsten carbide powders. And you see kind of two types of spatter. The globulars like this, we believe those are molten nickel droplets coming out. And the other ones that you see that are much smaller, moving fast, those are tungsten carbide particles. And for some reason that is not well understood, some of these tungsten carbide particles bounce off the surface instead of like coming into the melt. What happens is kind of weird, right? Imagine you go to a diving board and you cannonball into the swimming pool, and instead of going into the water, you bounce off, right? But that is what happens. So here we have an example of laser cladding. When you do laser cladding, and I mentioned you can add the material, the filler metal, as powders or as hot or cold wire, right? So let me discuss a little bit about wires. How do you put the wire, sorry, let's talk about powders. How do you put the powders in? So in this case, in these first three images, the beam is coming vertical, the laser beam. So one way of feeding powders into the weld pool is what they call off-axis. So it comes from this side. So the beam would be coming more or less here between the separation between the two figures. The weld pool would be at this level, and we melt this area with the beam, and we bring the powders on this side. So what is good about this is easy to access, and for example, if we have a beam that instead of being circular beam, it's a rectangular beam right? Because now a laser beam can have any shape we want because it's a matter of optics. If we have a rectangular beam, typically we want side feeding in that case. If we have a square beam, when the beam is not circular, we typically want side feeding off axis. Now, sometimes we have a circular beam and we're feeding coaxially, right? And there are two types of coaxial feeding. And by the way, this I'm telling you about cladding is exactly the same for additive manufacturing. In additive manufacturing, you have all these feeding schemes too. So one is what they call discontinuous coaxial. In this case, you see only three, but what is coming out of here, these blue rays here, are in reality jets of powders, right? And it has 4 jets of powders. The 4th jet is just behind this one and we don't see it. Our PTA torch in the lab has a discontinuous coax nozzle, but instead of having a laser beam, of course, has a plasma torch, right? And this is good for cladding complex geometries, and is something that is good about this is when we have coaxial, we can move in any direction we want and we'll be okay. With side axis, if I move from right to left or left to right, I'm going to have a very big difference, whether the powders are leading or they're behind, right? Because the weld pool is always trailing. So if I put my powders in front of the weld pool, most of them will be bouncing in the solid metal. Typically, you want to feed in the back. I just discussed discontinuous coaxial. About a continuous coaxial, in reality, it's not really true. Discontinuous has, let's say, 4 holes blowing the powders. In continuous coaxial, what you have is like 30 or more holes. So it's more or less the same, but when you have so many holes, they look as if it is just a continuous feeding. This is typical of coaxial feeding in laser cladding. And now we have a head like this. Other type of head that is typically would qualify as off-axis is when we are doing internal cladding. And when we do internal cladding, it's very difficult because now we have a very constrained space in which to be. And we have to put the laser optics, we have to put the shielding gas, and we have to put the powder delivery system all in a space that is so small that can fit inside a bore, inside a hole. And you can imagine that if you're putting any number of kilowatts through a little hole, through optic fibers and mirrors, in this case, typically there is a mirror because the fiber is coming this way along the shaft and then needs to be bent. If any part of the optics gets dirty, for example, because a little bit of powder fell on it, that part that contaminated the optics starts to absorb a lot of heat and creates a bigger problem. And every problem we have absorbs more heat, so we destroy very quickly our optics. The smallest we can do that can be done in the world today is of the order of 2 inches. It's about 5 centimeter internal diameter. Very small. And here we have a schematic of people doing wire feeding in laser cladding. And in this case, it's very uncommon. They have the wire is coming in the center and they're feeding light from around it. It's not very common, but this is, we are starting to see this type of configurations of wire and laser in additive manufacturing. For additive manufacturing in particular, here we have this, what people call 3D printing, right? Although that's a trademark, you can do it for wear and corrosion protection, and you can do it in remanufacturing. And this is interesting. Now we call it additive manufacturing because we're building features But we have been doing this for decades when we talk about rebuild or repair or remanufacturing. And this is interesting and powerful when we do this, because a part that would have been discarded, but is very expensive, now with a little bit of cost, if we have the equipment and we have the knowledge, we can rebuild this part at much lower cost using lasers. One thing that is not welding, but I want to bring to your awareness, is what is called laser heat treatment. So in welding, we need to melt. But let's say we don't melt. Of course, then we don't weld. But if we don't melt, but we're talking about a steel, for example, and our beam makes it go to the austenite range, when it cools down, it can turn into bainite, martensite, all these things we have learned from phase transformations. And lasers can do this localized heat treatment in a way you couldn't do it in a heat treatment furnace. So that's something that is done in our province today, and it's a technology that uses the same equipment of laser cladding, but for a different purpose and with a very good impact. So we can do the laser cladding to increase the strength of a component, to increase wear protection by giving it a higher hardness locally. We can also do things in which we do a local heat treatment and affect the ductility. This is a B pillar in a car. That is the pillar that goes right behind the driver's seat, and the one that protects the driver, or on the right-hand side, the passenger, if you have a side impact. Right? And of course, look, this is from Laser Line, one of the ideas they have about mobile laser units. This is not off-the-shelf equipment, but wouldn't it be totally cool to have a little tractor like this walking inside a big vessel and refinishing it quickly and automatically 24/7. All right. True or false? I like to hear what. All right. Have one. Yes, yes, yes. Thank you, you guys. You guys are paying lots of attention. You're super awesome. Okay, of course, it's false. It's high power, but high velocity. And the high velocity, like, more than distributes the high power that we have. Combinations, hybrids between lasers and arc. Typically, the laser leads the arc, and it would be the case of laser MIG or laser TIG. And in this case, what we have is that we can have the best of both worlds. The laser can give us the depth, and the MIG can give us a bridging of the gap. Imagine you're having a butt joint and you want to use a laser. If the joint has a gap, it's very likely that the beam will go through the gap and weld your floor, but not weld your plate. So if you combine it with MIG, MIG closes the gap, and even if the laser is leading the arc, the laser is aiming at the weld pool, and that gives you the absorption of the heat by the weld pool. Where is this used? Heavy sections, like, for example, pipeline, or for example, nuclear. People have been trying to do this in pipeline. I have seen it, but here's one of the problems. The steel for pipeline is designed to be rolled and thermomechanically processed, and that will give you a good pipeline. If you melt it, when it goes solid, it is nothing as good as the original material. It's typically very hard and brittle, especially for the very fast cooling rates of the arc. Now, of the laser. When you're doing arc welding, you still have a problem of solidification, but you have a filler metal that has a special alloy such that when it solidifies, it's good. Now, in lasers, if you do it autogenously, it's going to be ugly. But even if you put, you do a hybrid with MIG, what happens, and I know this for a fact because friends of mine were doing this in Germany, the filler metal stays close to the top, but the laser keeps drilling deep down. So you have good metallurgical properties where you had filler metal near the top, but deep in, where there was no mixture between the filler metal you added and the molten metal deep into the laser weld, that weld tends to be very brittle. I do not expect to see pipelines being laser welded anytime soon. I do expect stick welding to eventually phase out, but to be replaced by orbital mechanized processes like orbital welding, involving some variation of TIG, MIG, or flux core. Okay. The characteristics of hybrid laser can only be done automated, very high productivity. This is what you use in the auto industry. Very complex because not only you have all the pain of setting up a normal welding machine, now you have the pain of setting a laser welding machine that is even more difficult. And then you have to make sure that both are lined up and they have the proper distances. Very complex. So typically this is done only for very large amounts of manufacturing of the same thing, as it is the case of automotive. Has very low flexibility, but once it's running, can make these very, very fast welds. The weld in the end looks just like a normal MIG weld, just you made it so much faster than a MIG weld. The melting efficiency is also higher because you move so fast. You don't give a chance for the heat to dissipate into the rest of the base material. So distortions are lower. Where you use these? For large series in automotive or very high value added processes like nuclear. Let me show you a video. Remember when I talked about a fast weld? Check this out. And I've seen a weld very similar to this live in Austria. Right, there you have your hybrid thing. Is that faster weld, right? Very, very fast. That's what you want in automotive industry. I remind you, you don't see the laser because the laser is infrared. So in this case, you saw the arc, but if you didn't have the laser, the arc has to be much slower to melt the plate and have all the heat transfer that forms the weld pool. Let's switch to electron beam welding. And this slide looks very much like the one in laser because it is the same. Now, the only difference is instead of being a laser beam, we have an electron beam. But if the power is not very high, then we have what they call conduction mode and looks very much like TIG. If the power is too high, well, not too high, but if the power becomes higher and higher, you cause this local evaporation and you start creating a keyhole. Very much the same for most practical purposes. Now, there are very important differences between laser and electron beams. Number one, in electron beams, you tend to operate them under vacuum, either high vacuum or low vacuum. The Soviets tried no vacuum processes too. But in general, the electrons don't fly very far if there is a gas between the gun and the plate. So you tend to do it in the vacuum, which is a fantastic thing for materials like titanium that are so reactive with contaminants, very highly reactive. So now you have the best of both worlds. You needed a vacuum for your welding system, and you wanted the vacuum to protect your material. This is the way you weld jet fighters. Filler material. Very often, electron beam is done autogenously, very often. But if you want, you can add hot or cold wire. When I was doing my PhD in the 90s, one of my lab mates was doing what at the time was called rapid prototyping. We didn't have the word additive manufacturing then. And he was using an electron beam, feeding it a wire, a cold wire, making components out of Inconel 718. Right? And incredible problems of distortion as the build-ups were progressing. There was no software, nothing. It was so difficult to make. Isn't that incredible? Now, electron beam does not look at all to like arc welding, but it has a similarity. Now we have an electrical current, but while in arc welding, we have relatively low voltages, 15 volts, 30 volts, but more or less 15 to 35. From a little TIG to a huge, or 10 volts in a little TIG to a huge sub-arc welding system. And the currents are high, are 200 amps, 100 amps for a little arc weld, 1000 amps for a heavy sub-arc weld. Electron beam is the opposite. Instead of being 10 to 40 volts, now we have 150 kilovolts. Let me tell you, that's very, very, very high. That's a lot. Kilovolt, that's, I don't even know what to compare it to, but it's 150,000 volts compared to 25 volts, right? Very much. Conversely, the current is very low. While in welding we have 100 amps to 1,000 amps, now we're talking about 0.1 amp. Right? But if you multiply one by the other, you end up having lots of power, right? Much like in laser, it's true you have a lot of power, but you move fast, even faster in electron beams. And the resulting heat input then is low. What characterizes electron beam welding? Number one, it's even more expensive than laser, because in addition to all the expensive circuitry, all the expensive electronics, you need a vacuum chamber. And when I was doing my postdoc, I actually operated an electron beam welder. It's not that I became an electron beam operator, but I tried my hand. And it was something that was donated to my university by a company that was making fighter planes. And you could walk into the chamber. And it took forever to purge, right? Because once you load it, you have to create a vacuum, and that could take very long. Electron beam welding, as you can imagine, when it is so finely focused, has very low residence time, and can be then and cannot be done manually, right? So you're always going to see electron beam welding automated. Much like a laser, low heat input. Okay, electron beam welding can make the smallest details of all fusion processes. This is the finest detail you might want. Also, electron beam welding has an advantage over laser welding. When you shoot an electron to a material, it tends to stick. It's not 100% of the electrons that stick. You know that some are backscattered. That's how an electron microscope works. But those are relatively few. We will discuss how many are backscattered when we discuss efficiencies later on. But by and large, you shoot the electrons stick. So you have so much better efficiency than is the case with laser welding. Hmm? So when I mentioned you shouldn't weld by laser weld by hand, one is short because you have a very short residence time, and the other is because the reflections can kill you. But in electron beam welding, there's not so many reflections. If you defocus an electron beam, the residence time becomes longer. So applications, of course, electron beam welding is only shop welding, very high value added components. When I talked about the F-22 in our first class, in which I gave an introduction to welding, and I said how relevant it is for the aerospace industry. That's how it's welded. Pretty much all jet fighter planes are laser welded. Now, if I can defocus an electron beam welder, and I would have a longer residence time, and if I don't have a problem of reflections, that would be relatively safe. Why don't we sell? Why can't I buy from our welding suppliers a manual electron beam welder? Anybody can have a guess? Why can't I have a handheld electron beam welder running with the defocus beam? Okay, good. Thank you. The vacuum requirement. Let me show you something that is super, super cool. There you go, the vacuum requirement. This lady is Svetlana Savitskaya, is the first spacewalk by a woman. And you know why this lady took the first female spacewalk ever? Because she went to weld. And here's her welding gun. And she has a defocused electron beam gun, right? And yeah, space pipelines, there you go. And was awesome. Now, if this woman is the person we all aspire to be, right? She was an astronaut, like got the very, very high awards, at least for the Soviet Union. She had world records on MiG fighters. And in addition, she managed to be married and have a child. I think it's pretty impressive. Now, if you read more about her, there's something interesting, that she thought that this experiment was completely crazy, because if there was a little mistake and she cut her spacesuit, she would be a goner. So safety first, but they did it. And a funny thing, soon enough, the Americans wanted to do the same too. But right today, nobody is welding in space. I do anticipate that these type of things are eventually going to be in use as we keep expanding into space. And I think it's going to be awesome. And I'll be totally ready to pitch in when that happens. By the way, let me tell you something. The people who know about welding on Earth typically know what they know. But you, because you take the class, you might not know all the tricks, but you'll know why things are the way they are, and you'll know how to handle things if you have no atmosphere, or if you have no gravity, or anything else. So I think we're in a cool situation.
In electron beam welding, the coalescence heat is generated by the kinetic energy of a focused stream of electrons directed upon the joint. The electrons are produced by an electron gun, accelerated to high velocity, shaped into a beam by electrical fields, and then further collimated or made parallel and focused by an electromagnetic lens. This electron stream is developed in high vacuum, but actual welding can be performed in either high vacuum, partial vacuum, or standard atmospheric pressure. Because of the intense and concentrated heat generated, total heat input is low, minimizing heat-affected zone size and part distortion. This also allows for the creation of extremely deep and narrow welds. Additionally, joints inaccessible by other welding processes can be welded. Virtually all ferrous and non-ferrous metals, thin or thick, can be joined. Welding speeds are fast, and filler metal is not generally required. Equipment cost for electron beam welding is typically high, and welding is generally limited to machined parts assembled in primarily butt, corner, and lap joints.
All right, this is more or less up to date. You want to know something really cool? There are very few manufacturers of electron beam welding equipment in the world. One in the US, one in Germany. I'm sure there is one in Soviet Union. You know where there is one? In Vancouver. This is German guy whose dream was to move to Vancouver and found that he could make a living by making electron beam welders. Who knew? It's right next door. We have a factory of electron beam welding machines. And the cool thing about those are that they can have a even narrow, tighter electron beam spot than most other welders. Go Canada. All right, so this is about beams, and I'd like now to switch to resistance welding processes. And if you have any questions, you can ask me as I try to switch the slides here.